Welcome everyone to our final class on MetaPlots, where we're going to bring it all together. We're going to bring in clustering and binding profiles over promoters that we just did previously and make some pretty heat maps of them and some other cool plots. So we're going to continue to reiterate using our skills where in the last class we made a set of 36,000 promoter windows for a metaplot of like making them in a line and asking how often a peak overlapped that position of a promoter. And so we could find the trends of how a peak bound, if it bound over the start of the gene or to the left or to the right. And we're going to look at that more today and do it iteratively and also make a heat map and cluster them. So previously, we clustered our ChIP-seq data by what type of promoters they overlapped, how similar the promoter overlaps were. And now we're going to cluster them by how they bind across a promoter window of 2 kb. Okay, so let's get started. I'm here in class 2023, 05 R analyses, MetaPlots, and MetaPlots 2. And this is the code I'll be reading from in our studio. But if you are on the web at lncRNA.io teaching, we're here in number 7, MetaPlots, finishing it up and going to move on to RNA-seq after this. Okay, let's start by loading our environment here. I've already loaded in my packages that we've used before, and I'm going to load in the environment of peak features in 01 that we made as sort of a handy repository of our ChIP-seq consensus peaks of all the peaks that overlap in our replicates are in here. And it's a little bit overboard to load it. Just really what we're loading this for is our consensus peaks here, which is each of the DNA binding proteins ChIP peaks that are common in all the replicates. Okay, and so we essentially, last class, the exercise was to take the class and make it a function. This is a really handy function. I use it all the time, to be honest, and I think the cool plots we'll see in a little bit will hopefully motivate you to go back and make it one. But if you clone the class, you probably have this in your util in class 2023 where you cloned it. In the util, you have this my class functions here. If we look at profile TSS, it's exactly the same code as last class, setting up the parameter of what is your peak consensus peak file, what are the promoters or what gene features do you want to overlap with, how much upstream and downstream. And then we made where our peaks overlapped 1s and 0s across the genome. And we're using integer range lists instead of G ranges, made the same for promoter windows, overlapped those promoter windows, and then stacked all the promoter windows and quantified how many overlap events there were per column, which is a position in the promoter window. Okay, so I made that a function, and these are the parameters. These are the default upstream and downstream that to be used that I'm using. So we can just run this now. It takes a second, but it's not too bad considering all that code we had to write. We would never want to keep writing that over and over again. And I can now just quickly make a metaplot of how my DBP binds over a promoter. We'll make this much prettier later. But for now, we can just see that EP300 has a binding where most of the binding overlaps with promoters occur at the middle of the promoter, and there's less peak overlaps at the tail end of the promoter. Okay, so now let's start. We could do that over and over again. We're going to skip that. Feel free to run each of yours and save them if you want. But what we can do now is run a for loop. So now we have a function, so we can say I through length consensus peaks here. So for each of these consensus peaks, run profile TSS and intersect it with long non-coding RNA and mRNA promoters that we've made in 01 peak features. Okay, so this is a G ranges. and this is a G ranges, and it's going to then change it in integer range space, find the overlaps, and give us a density of data at each position in the promoter window over all of our peaks. Okay, so we're going to just see what that looks like. So what we're going to ultimately do here is set up a data frame that's going to take the output of profile TSS and fill in integer and density and DBP, which of the 7 proteins I'm studying. Okay, so let's just set that up for posterity, and then, oops, missed some indices there. So let's just run this line and set up that it's an empty data frame here with 3 columns. The integer, which is the position in the window, density is the value in the window at that position, and DBP is the name of the ChIP-seq file. Okay, so let's test one of these out running profile TSS just to refresh what we get out of that function here. And it's a pretty simple output, which is X is the position in the window. So from 1 kb upstream to 1 kb downstream. So this is going to be 2000 long because we just did the one DNA binding protein HDAC1, just to see what it would be like putting this through a for loop. What's it going to see? Okay, so we have the position and the density of overlaps at that position, sort of what we see here, where the density would be high and the density is low on the edges. And so I did that for just one by indexing consensus peaks into just HDAC2, just to get a peak of that. So we have what's going to happen here is 1 through length consensus peak, which is my 7 G ranges of peak things. This is just a printout to see its progress of which DBP is on. When we do a bigger data set, this will be really useful to see where it is in the process. And then we're establishing a temporary data frame here where we run profile TSS. So from there, we're going to get X in density. And we're running profile TSS with the consensus peak that is in the for loop, and again against lncRNA mRNA promoters, which are the parameters for profile TSS. Okay, so we're going to get 2 values there, and we're going to now make a 3rd column called DBP by indexing into a column we want to create. And we're going to just do the names of consensus peaks, which is the names of the DBPs or the DBPI that's going through. And then we will bind the rows of that output here with metaplot df, which is what we established as blank. And so then it'll fill in 1 row, go to the next DBP, fill in the next row, fill in the next row, etc. Okay, so let's take a look at what that looks like. It's going to take a second to run. So it's printing out which value it's on here. So it's on the first one, and it's basically making this whole plot data and then repeating the process for each of the DBPs I chose and you chose. So if we run this for 480, it does take a long time, but it's a very robust function that can do 1 metaplot or 7 or 480, depending on what you want to do. Okay, so it should be finishing here. And we will take a look at metaplot df. Okay, metaplot df just showed up. So it's 14,000 long. So there's 14,000 rows. And that's because I have 7 DNA binding proteins, and there's 1 through 2,000 of the window. So the window is now this way for each DBP of -1,000 to 1,000, then the next DBP, and so on and so forth. So that is the output of our for loop. So now we have basically the same data we have for this for every single one of our DBPs in here. And so we can write that out because we don't want to have to run that every time, especially if we do it for a lot of them. I'm going to make sure I'm in the right working directory. Oops, I just set that as working directory, which I did not mean to do. We are in classes 05, metaplots 2, and I'm going to set this to my working directory, so that I print it out into my results folder here. Okay. Cool. So then we're going to read it in. And the reason to do that is also the column to make sure the column names are the same when you read it back in. So we're just going to read it back in, because read underscore RDS may put different values there, and you might want to double check that. So now what we are going to do is pivot wider. So we have this long thing of 2000 values for each DBP going down. What we want to do now is make them come up as columns, so that we can have the position and then pivot wider, so we have more columns, one for each DBP. And so we're going to do that. I'm just going to make sure I read that in. And we're going to look at pivot wider and pivot longer. They're really useful. It's a little bit complicated, but highly worth spending some time really digging into this. So we're going to pivot wider and actually make the columns now the position. So names from is saying, okay, what do you want the columns to be from? And it's X now, which is our position from -1000 to 2000. And the values from density to be the row that's filled in. And then let's take a look at what that looks like. So now, if we look at our metaplot df again, here it's really long, -1000 to 1000 for each DBP. And now we're going to pivot wider and call it a new name, metaplot filtered matrix. And we'll just run that for now. And now if we look at metaplot filtered matrix here, what we see now is the position is on top, and each of our DBPs is a row. But we don't, if we're going to cluster, we don't want this character to be in here. So we're going to make the row names the names of this column here, DBP. And so let's look at what happens there. If we do column to row names, we're just going to shift those to the names of the rows instead of actually being values in the column DBP. And then we're just going to pipe it to become a matrix. And if we now look at, let's look at it before doing that. So it's easier to read. Now, if we look at metaplot filtered matrix, we see that the names have moved over here as the row names rather than being a value. So now we can do clustering, which we did in a previous video, where we can now say how similar are these rows to each other using a distance metric. And so that's what we'll do now. But first we'll make it a matrix, so that now it's just going to be those ones and zeros as a matrix, and then a meta tag of the DBP name. Okay, so let's see if there's any NAs in there. This is just a extra check. No, I don't have any. And so now we're going to take our metaplot filtered matrix, which we just put the DBPs as row names and have ones and zeros at each position along the promoters. So now we're going to make this object scaled, where we're going to take our matrix that's now 2000 wide, and we're going to tip it long and scale the rows, or the columns, sorry. And that's what the T is doing for transmute, is we're going to take it wide, tip it over, scale it as columns, because you can't scale as rows. So it's just a bug you're going to have to figure out at some point. And scale it and then tip it back the way it was with another transmute. And the scaling, what's happening is it's taking the average number of ones in a column, and then dividing each position in the matrix by the total number of ones. So it tells you sort of the percentage of ones, or the density of ones in a given position. So right now they're ones and zeros. And then if we run this and look at scaled, what we see now is we see these negative values and positive values. And essentially what we've done is said, here's the average across down this column what is your value above and below that average? And this is going to allow us to make a heat map to say, like, what is the average binding and where is binding up and down below average, is what we just did with scaling it here. It's called row scaling, or in this case, we have to do column scaling just because scale requires that there. So then now scale gives us sort of that value averaged over the number of overlaps for each DBP's row. Okay, which was a column in the middle. I know that's kind of confusing, so just go back over it and sort of think about it. But essentially, we take it, tip it, and take each column and normalize it to the mean number of values in the column, and then say, what is your value above and below that? And so we have something for a heat map. Okay, so now we are going to use our hclust and find the distance from these normalized. Our matrix is now back long with -1000 to 1000, and the values in there, instead of ones and zeros, are a normalized value across the position. So the rows are the DBPs, and we're going to cluster those with the method complete in hclust after we calculate the distance of each DBP's pairwise rows. So if we look at dist scaled, what we can see is, again, this sort of handy comparison of how similar each DBP is to the other one. But we're now doing it by where it binds in a promoter rather than which promoters it binds. Okay, so let's cluster that. And then we can just use plot to plot that distance matrix, metrics that we just looked at here. And now we can look at it and see, oh, we see a different pattern now where these two are very similar to each other too, but there's a little more definition between these. And these two are known to sort of work together, and that's kind of interesting that they have similar binding profiles. But we haven't seen the binding profiles here. We're just comparing how similar they are to each other. Like, do they all look like that, or do they have, how similar do they look to each other? Does this image look to the other images of each DBP? Okay, so you can then save that if you want. And then let's sort of dig a little deeper into clustering here, where we can use cut tree to say how many clusters there are. So when I look at this here, I could say, well, I see 2, maybe 3 clusters. What are the number of DBPs in each bin? And so currently I have 7 by default, but if I break that into 4, I can then look at table of how many DBPs are in each cluster, and I can see, okay, cluster 1 has 3 and cluster 4 has 2, and these two are more different. So I'm separating this out pretty well, and you can play with this and add more. And then what you don't want is all of them in the same bin. And so I've already optimized mine for 4. This doesn't matter. This is what you really want, is the unbiased clustering of the full thing. But this is just to show you how you can zoom in on a specific cluster and make a heat map. Okay, so let's do clusters cut tree, make a value for k equals 4, and now we have them clustered into 4 groups. And this is just some coloring and how to split the data frame by the promoter window. It's not a big deal, it's not required. And so now what we're going to do is run heat map from complex heat map. And what it needs to know is a matrix of values. Now we have normalized values, so we're not doing binary. So we don't have just zeros and ones anymore. And it's been normalized. We are not going to cluster the columns, but we're going to cluster the rows, which are the density function that you'll see in just a second. So it's going to cluster the rows by default, but we're turning off clustering the columns. And so here we go. And so what we can see here is that we're clustering by each of the DNA binding proteins, similarity here. And we can see that these two are very different and from everyone else. And we can now see that much better if we zoom in here, that indeed these have like orthogonal, where this one, it binds to the right side of the promoter. This one does not bind in the middle, whereas this group up here all bind in the middle and are probably just different because of how far wide they bind. And so you can think of this is the same line plot just as a heat map. And so where there's more density, it's more red, and where there's less density, it's blue. And we normalized it so that we could say where is the density above average and below average for my DBP, because the peak files could have different properties. So we normalized each of these rows, even though it was tilted as a column when we normalized it. Okay, so that's a pretty heat map, and really cool data to know that K27 trimethylation does not like to bind near the TSS. Most of the other ones do, and K36 is in gene bodies, which is actually known. And so that's a validation that this chip data is showing us what is already known there. Okay, so you could pick out a single cluster where you could do scaled and do our square bracket subsetting, where we're just going to take out only the rows in column 1, which is, I think, 3 from our table before. And we can look at that. And yep, it's 3. And we can see these are the 3 that are in cluster 1, and they all look very similar. So my clustering is doing pretty good, and this is just a way of QCing it. But really the unbiased full plot is just as fine too. Okay, so we are going to now make MetaPlots for lncRNA and mRNA promoters separately. And really what we're doing this is to relearn the same skills again that we just did, and just a little bit different of a question, and say, does this binding profile over promoters change between long non-coding RNAs and mRNAs? And so to do that, we are going to take our lncRNA and mRNA promoters object that we've been using over and over and subset it again to just gene type equals long non-coding RNA, using the square bracket indexing into gene type of the same object. So we're just taking half of it basically, and the same for protein coding here. So we'll load those as separate values. Now we're going to run the same thing for each one of them separately and make these plots. And then we're going to do a trick where we can plot them together, separated by long non-coding RNA and mRNA. Okay, so let's do that. And so we're setting up again an empty data frame for the long non-coding RNA metaplot DF. So we're really doing the same thing, just seeing it a little smoother now with doing it again. And so here, X is our position, density is the density of the data and the position, and DBP is going to be the name of our ChIP-seq consensus files. And this is the same for loop where we're going to print out where we're at in it, make a temporary data frame where we use profile TSS to get these first 2 values here. And then we make another column in that temporary DF inside the for loop, which is the name of the DBP that's being run through the for loop. And then we bind the output of temp DF, which is now 3 rows, into the 3 rows we made in the data frame, and it'll do that for each iteration of the for loop. Okay, so we have made our promoters, and now we're setting up the generic data frame here and loading it. And this will take a second, but it's good to go over here. I think one different thing from above, really it's all the same, is that the parameter for profile TSS is lncRNA mRNA promoters, and we just set it equal to lncRNA promoters that we made right up here above. Okay, And so that has run, and now we're going to do the same thing for mRNA, same values set up in the empty data frame, but now we are going to set lncRNA mRNA promoters to mRNA instead of lncRNA and run profile TSS, and then merge that into its own metaplot DF. Okay, sorry, I've already done that, but can't hurt. And now it's printing out where it is. And so now the trick we're going to do is we can look at the lncRNA metaplot here. lncRNA metaplot DF. Yep, here we go. So if we look at it here, we can see it's the same thing, 14,000 long, 2,000 for the position in the window times 7 DNA binding proteins. But these are only long non-coding RNAs in this object. So we could put a column here that says long non-coding RNA, do the same thing for mRNA, and then bind them together. And we would have a column to facet our figures by. And we can revisit our faceting skills from ggplot. Okay, so now we can look at mRNA, mRNA metaplot, same thing, position, density, and DBP name, but these are only mRNAs. We just separated them in profile TSS. So let's add the gene name here and look at mRNA metaplot that we just looked at. Now we have a column here that says for all of these, every entry is the same, but we've tagged them in a way. And I think this is an important thing that is done often, is separate them, tag them, and then plot them together and separate color by that column. So we're assigning an identifier essentially. And the same thing for the long non-coding RNA metaplot. And now we're going to combine it with bind rows here and just combine these two into one. That should be 28,000 long, 14,000 for each one. Yep, 28,000, and it now has the gene type of each one and the DBP in there. So the more we can put key identifiers, then the more things we can plot by here. So really the key thing, this looks complicated, most of it is just titling. But there's a couple things to point out here is now we have this combined metaplot profile for ggplot. Okay, great. Set the x-axis as the position along the promoter window. Y will be the density or the sort of profile. And we can color by gene type now. In our combined metaplot, we have the gene types mRNA and lncRNA in there, so we can separate them colored there. And then we can use facet wrap on the DBP column and make a plot for each one of them separately. It's kind of like magic. I think faceting is great. So we can go in and say, after you've done those functions in ggplot, now make one for each unique entry in DBP here. And so it'll split them into their own images. Okay, so let's take a look at that. That's really all we're doing there is we're faceting by the DBP column, and we're doing it in this same place. We're not adding other information to compare to. And so let's run that. And this is cool. Okay, so whoa, cool. All right, this is a lot of data here. So we can see that these all look pretty similar between long non-coding RNA and mRNA. Long non-coding RNA is in black and mRNA is in red. If we look at this H3K27 here, that's really interesting that at mRNAs, it's depleted and it seems to go across the TSS for long non-coding RNAs. Here we can tell we don't have much data and would be kind of suspect of doing that. This is amazing that just by running one function across 7 ChIP-seq consensus files, we can now see the profiles around a promoter and how they're different between lncRNAs and mRNAs. And mostly they were the same. So that is awesome, in my opinion, that skills to learn and go back and say, like, it doesn't have to be promoter windows, it could be enhancers, it could be gene bodies, it could be whatever you're interested in. These same concepts would apply to that, and you could end up with plots like this by running the same code and thinking about the same principles. All right, with that, thank you very much. And until next time, be well.